Okay, dear students, in this video we will see how to write the matrix of a total derivative. I mean, matrix is representation of total derivative of vector fields. In the last video we have seen how to construct the matrix representation of any linear function. Now today we have linear function total derivative. As you know, the total derivative of a vector field is always a linear function, linear transformation, linear map. So we can always construct it as matrix representation. Why actually we are interested to construct the matrix representation of total derivative? The fact is that the total matrix representation of total derivative of vector field is nothing that is the Jacobian of the vector field. Okay. So let us suppose we have f, let f from S contained in Rn to Rm be a differentiable vector field, differentiable vector field at A belong S, where of course A is interior point of S. So A is interior point of S, F is differentiable at A, it's a vector field. I want to see the total derivative of F. We know from the last video we have seen, in this case the total derivative of F at A is actually the directional derivative of F at A in every direction. Then TA at Y is equal to F dash of AY for every Y in R of N. We have already seen there, this is also equal to summation K run from 1 to M delta of Fk A dot Y into Ek for every Y in Rn. So this is our total derivative. So I can say the total derivative TA at Y is equal to, I will expand this, it will be delta of F1A dot Y plus delta of F2A dot Y, of course, into E1 into E2 plus so on plus delta of Fm A dot Y into En for every Y. Where you know this E1, E2, so on, Em is the basis of Rm as m dimensional vector space over R. So this is the basis there. Now T of AY, TA is a linear map. TA when applied to Y becomes a linear map. I have to construct it as basis. This matrix representation. For that, what I have to do? Simply select the basis of Rn. Usually we choose the standard basis. Then evaluate TA at every point of the basis. Then express that as a linear combination of the basis vectors of Rn. Then take the transpose, we get the corresponding matrix. Okay, let me call this as 1. But you know what, this gradient of F1, I will give you the value of this one. If we choose, if G is any scalar field of n variables, say x1, x2, so on, xn, or simply you can say G is a function of n variables which are x1, x2, so on, xn. Then remember, when we apply this delta to G, it means del G by del x1 del g by del x2 so on del g by del xn. This is the meaning of this gradient. When I write gradient of GA means I have to evaluate this n vector at a point A. Del G by del x1 at A, del G by del x2 at A, del G by del xn at A. And I write A there. So del F1A will be simply del F1, delta of F1 at A will be del F1 at A by del x1, del F1 at A by del x2, so on del F1 at A by del xn. There is a meaning of this gradient of this one. This I need in the construction of matrix. Here I have the basis of Rn as EIs. I will write the basis of Rm is EIs, E1, E2, so on, En. I will write the basis of Rn in terms of some other notation. Let I will choose some other notation, say U1, U2, so on, Un be the basis of Rn. Of course, can say standard basis of Rn, be the standard basis Rn. That is generally U of I will be equal to 0, 0, so on 1, 0, so on 0 with 1 at ith place. These are actually the same EIs, but to use these here, these EIs are for Rm, I will use UIs for Rn. And you should remember these EIs, E1, E2, these are M vectors. Each is M vector. M tuple, this is M tuple. Here I have again such EIs, but now in this case this is N tuple. There are N components in this vector. To get this matrix representation, I have to evaluate this TA at every point of the basis vector. So what is TA at U1? This will be delta of F1A dot U1 into E1 plus delta of F2A dot U2 into U1. You are replacing Y by U1. Then you have into A2 plus so on plus delta of Fm at A dot U1 into En. Then TA at U2 will be similarly delta of F1A. Now you are replacing U2. Y by E2, so it's C1 plus delta of F2A dot U2 into E2 plus so on plus delta of Fm A dot U2 into Em, then so on. Finally, I have TA at Un, nth vector, that is delta of F1 A dot U N E1 plus delta F2 A dot Un E2 plus so on plus delta of Fm A dot Un into En. We can see T at A U1, TA U1 is trivially the linear combination of all these EIs, where EIs is a basis of Rm. It trivially becomes the linear combination. When it is a linear combination, there is a linear combination. So our matrix will be, therefore, matrix representation of TA with respect to the same basis this one, and the bases, what are the bases of Rn? We can write that E1, E2, so on, En, with respect to these two bases. I have not used the name of these. With respect to these bases, the matrix will be, simply take the transpose. We have delta of F1A dot U1. Of course, this is a scalar quantity here. As I told you, when we evaluate this delta F1, it's actually the first component of F. F is a scalar field. Okay, I can drop this. I have actual F. Actual F is F1, F2, so on Fn, because F is actually from Rn to Rn. It's a vector field. It's a function of n variables, means each component is a function of n variables. This is a function of n variables. This is a real valued function of n variables, real valued function of n variables. When I evaluate delta of F1, same way as we did for this G, delta of G. Similarly, we will evaluate delta of F1. That will be n vector, because it is a function of n variables. U1 is the point of Rn, it's n vector. Take the dot, you get a scalar quantity. Because you have to evaluate this at E. This will be independent of any variable. This is really a constant. So dot will be constant. This is constant vector. This one will be a constant. I mean a real number. Similarly, this is a real number. Delta of F2. Sorry, I have to take the transpose. So here I have delta of F2 dot U2, then so on, then delta of Fm A dot U of 1. It's 1 here. These scalars in a column. This scalar, this scalar, this scalar. The second column will be this scalar, this scalar, this scalar. So it will be delta of F1A dot U2, delta of F2A dot U2, so on, delta of Fma dot U2, then so on. The last column will be transpose of this row. That's delta of F1A dot Un, delta of F2A dot Un, then so on, delta of Fm A dot F. This is the matrix representation of TA. Now let us evaluate these entries of the matrix. Let me go to the first one. When we evaluate delta of F1A dot U1, what is the value? Because this is a function of n variables. So evaluate, this will be delta of F1 at A by delta of x1, delta of F1 at A by delta of x2. F1, this time instead of G you have F1. Simply replace G by F1. In that formula you get delta of F1 by at A by delta of xn dot 1 0 so on 0, because you have the first vector here. Similarly, when we go for this one, okay, let me go along the row column first of all. When we go to this place, we have F2s everywhere. The remaining is the same. So what is the value of this one? Its value will be, when you take the dot, all others are 0, only first will remain there. That is delta of F1 at A by delta of x1. Similarly, when you go for delta of F2A dot this one, u1, you will have delta f2a by delta x1, delta f2a by delta x2, so on, delta f2a by delta xn dot 1, 0, so on, 0. This will be taking the dot, only first component is there, that's delta of f2a by delta of x1. This will be for the first, so along the first column you have the partial derivatives of the components of f with respect to only first variable. Similarly along this you can evaluate, you have to choose here u2, in case of u2 you have to choose 0, first to 0, then 1, then 0, so on. Then you will get the second partial derivative with respect to second variable, because in every vector the second variable is x2 partial derivative with respect to second variable, that's delta of f1a by delta of x2. So generally I can say, generally what's delta of fi a with respect to uj, then you can substitute i's and j's, so you will get all the components. So this is the ijth element of the matrix. This will be, see, if you have I and j equal, so if I and j are equal, then it will be, suppose I is equal to j, means this is the situation. So you will have the first variable, so you will have like this, delta of fi a by delta of xi, if you can say j equals, j is equal to I. Well, I don't think this way. See, if we take the dot of these two, when we take the dot of these two, actually this matters. Here you have 1 in the first place, at the first place you have 1, so it is this one. If 1, so it is partial derivative with respect to first variable. Suppose 1 is here, if you take the second vector or third vector, suppose you have second vector, if you choose like this one, you will have 1 here, so you will have 0, 1. When you multiply, 0 will be this one with 0, then 1 with this one will be 1, this delta of f1 by delta of x2. This actually tells us with respect to which variable you are actually differentiating. So this is simply this one, for every I and j. For every I and j. Function ith, j corresponds to this vector uj. You can verify this. When I and j are equal, I is equal to j, or you can say I is 1, j is 1, you have this. If you go for this one, okay, let me evaluate on this side, so that let me evaluate this, delta of f2a dot ut. Delta f2 means del f2 at a by del x1, del f2 at a by del x2, so on, del f m at a by del xn. It's dot with u2. What's that? 0, 1, 0, so on, 0. What is the value? When you take the dot of these two, this will be 0, this will be del f2a by del x2. So del f2 at a by del x2. This. So this delta f1 fi at a dot uj is del fi at a by del xj. Substitute these values here, you get. So substituting these values, using the above values, we get we get TA, matrix representation of TA equal to del F1 at A by del X1 U1 vector. So it is del F2 जो भी function है by del X1 so on del, here you have mth component of the function with respect to the same first variable. Then you have del F1 A by del X U2. So for second variable del X2, del F2 at A by del X2, so on del Fm at A by del Xm. Then so on, then del F1 at A by del Xn, del F2 at A by del Xn, then so on, because last column corresponds to the mth vector, nth vector. So you have del F del Fm at A by del X. Sorry, here it's 2, x2. So this is the matrix representation of the total derivative. Matrix representation of total derivative. So if I call this as, say, this has a special notation. I will not write generally that way A, because this is associated with the functions. I will denote this by df at A. This is simply the notation. Then this dfa is called the Jacobian matrix of the vector field. The matrix dfa is called the Jacobian of the Jacobian matrix of the Jacobian matrix of the vector field F at A. Vector field F at A. Thus we can write, therefore. Now this is a matrix here, matrix representation of total derivative T. So the action of total derivative being a linear map, action of TA at y must be same as action of this matrix at y. So you can say dA at y is equal to dFA of y, where y is a point of Rn. So this actually tells us how you can calculate the total derivative. Forget about this y. So this quantity is the total derivative, but in the matrix form, matrix representation of the total derivative. Otherwise, it is very difficult to calculate the total derivative for all possible functions. So when you write in the matrix form, or when you want to calculate the total derivative of the function in the matrix form, you have dfa equal to this. So simply the partials will give. Partials will give us the total derivative. Okay, this is the matrix representation of total derivative. Thank you.